I get those reports, you're the first score I'm gonna look at.
Then lower the current.
And you're gonna be a senior next year, and I will hunt you down.
Lower the current.
You're gonna make AP Chem everything else.
Oh, you're gonna have to do it like in Latin
Resistance doesn't matter.
or German.
Because
Okay, Danny.
German.
Good. All right. So I don't know what happened. Deacon, if you're watching this, don't know. But we're gonna move on. Okay, so let's talk about some of these. And here's the wonky part about electricity. Is that, especially when you're dealing with like household current, one of the things there's any number of things you have to look at. Is it in series? Is it in parallel? Is it AC current? Is it DC current? Do you keep the voltage the same? Do you keep the current the same? What are you doing, okay? Because that all impacts these calculations. So there's just certain assumptions that you have to make. So let's start with question number 18, okay? So here's the story. So this one has corroded.
Finally.
I literally just marked you absent.
I got stuck behind the train on 45th Street.
Huh?
I got stuck behind the train on 45th Street.
there's a train.
Oh, you go that way?
Absence by
Yeah.
train.
It was the longest train I've ever.
Hold on, let me
The
change.
one and a half mile long trains now because they want efficiency.
Clearly not.
Okay.
Clearly not.
Now that Deacon has arrived, let's continue the story. So on number, because these all kind of build off of each other. So on 18, you got explain why the resistance of wire increases as it becomes corroded. So you have to understand what happens when something becomes corroded. So typically what happens is that you have iron, whatever, copper, and as it becomes corroded, that outside material changes either its chemical structure, where it doesn't conduct electricity as well, or it actually physically like becomes smaller, like it flakes off. Here's the whole point of the story. Is that what's going to happen is that the interior portion of that that's able to conduct electricity and conduct an electric field through it, whether it's physically becoming smaller or if the outside layer is becoming corroded and it loses that ability to transmit that electricity, your functional cross-sectional area is going to become smaller. Well, your rho isn't going to change because of the fact that that's a property of the material. Now, the only time rho changes drastically is when you change the temperature. So unless you're talking like extreme temperature changes, you just assume that that rho value is just going to be the same. Now, where it gets weird is that once you drop that temperature like far enough, then your resistance can effectively become zero, okay? But that has to, you're talking like the liquid helium, liquid nitrogen cold. I'm not talking like, oh, we'll put it in the freezer and we'll have these superconducting materials where there has no resistance. You've got to get these really, 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 really cold. Now, when you get to 19, and this is kind of the same idea. So 19 atoms boil off, otherwise known as corrosion, and these are the old style incandescent bulbs where you've got a wire that heats up. Okay, so this is going to be important. How the old, not the LED lights like these, okay, and this is the argument for LED lights, is that that filament, because of the fact that it always is running so hot, if you've ever tried to like change the bulb on incandescent, the old style bulb, like right after it goes out, or mess with it, they are incredibly hot. So because they're so hot, you're basically wasting a lot of thermal energy. So within that filament, if they boil off, and again, your function area becomes smaller. So the key assumption that you make on 19 is that how does this affect the brightness of the bulb? So there's two things you need to consider on 19. One is PIV, okay? Oh, power equals current times voltage. So American households run off of a constant voltage of 120 volts, okay? So you're not going to change the 120. You just, no matter what happens, boom, you screw the light bulb, you're at 120 volts. So here's the next step. So if you consider the fact that you have constant voltage, whatever that number is, then as you boil that off, and this is why I said these build off of each other. So on 18, you boil that off, the cross-sectional area becomes smaller, your resistance goes up, therefore your current goes down. So then with the same constant voltage, with a smaller current, you're gonna reduce the power and it's not gonna be as bright, okay? Does that make sense? Cool. All right. Now, let's talk about 21. 21, you kind of have to think through like kind of 3 or 4 different things. So this is how you have to start on number 21. It says, if you're operating at the same voltage of 120, the beginning of this, what?
Sorry, I was not fine with the last question. So why do bulbs flash really bright right when they go out?
I think it's just because it just probably has like a power surge.
The front of your,
Like, are you talking about the old style incandescent bulbs?
Yeah.
I think it's just so, I'm thinking it's just like on the verge of going out and you just get like, for whatever reason, you get a power surge that goes through. It shouldn't. I've just known them to like pop and go out.
Huh.
I've never seen one,
Like a flash?
yeah,
Like blowout?
yeah, no.
Huh.
Could happen, I'm just saying I've never seen it.
I'm gonna make a few weeks, so.
No, just. Okay, so on 21, so let's go through your thought process. Now, like I said, the beginning of this argument makes sense. So if you consider the same voltage, okay, and the traditional idea is that the 100-watt bulb is brighter, okay, and you remember this when we do labs, okay, when you're comparing brightness of bulbs. So if you consider on the assumption that the 100-watt bulb is brighter, which means it is consuming more power. So, and again, this is the key assumption, your voltage is the same. So the only way that you can produce more power then with the same voltage is if your 100-watt bulb has less resistance, which again, in some ways is counterintuitive, but it makes the math work, okay? So the 100-watt bulb has less resistance. The 60-watt bulb has more resistance. So that's the baseline that we have to establish. The 100-watt bulb is going to have less resistance if the voltage is the same. So here's the thought process. So let that resistance, let's just make up a number. Say that's 10 ohm, and let's say that's 15 ohm, whatever it is, just pick a number, 10 and 15, okay? So then here's what they don't do a very good job of laying out, is that if you take those exact same bulbs with a 10 ohm and a 15 ohm, and you put them in a different circuit that now has the same current, okay? So the 60-watt bulb is still going to have a bigger resistance. The 100-watt bulb is still going to have a lower resistance. So that's what they did a poor job of articulating in this question. The fact that you're going to take the exact same bulbs with the same parameters that you just established. So once you get that idea, then you go, okay, same bulbs. The 60-watt bulb is going to have more resistance. So now if you look at power equaling I squared R, if the current is the same, then the one with the bigger resistor is going to produce or consume more power, and that will become the brighter bulb. Okay? So that's what I wish they could have added to that question. Like, okay, take the same bulb, now you know the relationship between the resistance, now plug it into a circuit where you have the same current. Okay? Does that make sense? Okay. Now, when you get to number 26, and I think this is the voltage or the speaker question, okay? Creates a 5-volt potential difference across the speaker. To double the power output of the speaker, the amplitude's potential difference must increase. Right. Okay. So here's what you've got to assume on number 26. So if you look at power equaling V squared over R, okay? It really doesn't make any difference what you have in your value. Here's the whole point, is that it's V squared over R. So what's gonna happen then on 26, to double the power output, you wanna know what has to happen to the potential difference. So the only way that works then is if on that one, you wanna double that power, then you look at that V squared over R, and because of the fact that that's V squared, that's going to, and if you think about it, it's like, oh, hey, we wanna crank out more power, we want louder speakers. Hey, the only way that can happen is if you increase the wattage going into that, and you just have to assume that the resistance stays the same. Alex?
And so why not the argument about power equals IV? Because, oh yes, resistance to power, you can probably change
The assumption is that you're keeping the same resistance.
same resistance, same resistance is constant, current changes.
Yes.
Oh,
Okay. Let's talk about some of your answers. On 36, this is a huge-ish, okay? But on 36, both of your answers should be around 10. Okay? It's an ish, but they're around 10. On 38, this is also an ish, but on 38, those answers should be around 4. Okay? Gapshawn would be flipping out at these answers, but guess what, Gapshawn? You're not here. On 40A, that's assuming they'd watch this lecture.
Yeah, you probably won't.
Yeah. On 40A, because if that kind of goes south, everything is going to go south. Your answer to 40A should be around the number of degrees in a circle. Around. It's an ish. Could be elliptical, but yeah, something around there. Now, let's talk about number 44. Okay? So this is where, oddly enough, dealing with the fish tank, this is where wattage becomes an issue. So if you look at that fish tank at the end of the hall, and by the way, if you ever see anybody putting anything inside that fish tank, let me know, because I'm going to track them down and strangle them maybe. So the temperature has to be maintained at about 77 degrees Fahrenheit, right? So if you go and look at tank heaters, there's like 100 watts, there's 200 all the way up to 400 watts. So what's the difference between those tank heaters? 100 watt versus 400 watts. More watts.
More power, more energy.
Yeah, there's more energy per unit of time. Okay? So if you want to heat up the tank quickly, obviously you're going to use
Higher wattage.
higher wattage because that's going to produce more energy per unit of time. So if you look at trying to keep this thing at 77 degrees, well, the room temperature pretty much in the school is consistently low 70s. So if we don't have that tank heater in there, then eventually that water is going to cool down, and that's what happened. I didn't realize with the tank heater. I quit working even though the little indicator light said that it was, and the temperature dropped too far. So on number 44, here's the two things that you need to do on number 44. You've got ice, okay? That's at minus 10 degrees Celsius. You're going to make it melt. So, Jane Carroll, what's the first thing I have to do to make the ice melt? Huh? add heat, to raise the temperature to 0. So if you remember back, way back in the day when you were in that right before Christmas, you're like, oh, the simple days of physics. Okay?
That was the wisest.
And we talked about a temperature versus like time graph. And we're starting here at minus 10 degrees Celsius, and we're going to dump energy into it, okay? And remember, whenever there's a slanting line, so this is old school review. Anytime there's a slanting line, that means that the energy is going in to change, if you think about it, the kinetic energy of the particles. Because remember, temperature is like a measure of speed. It's how fast the particles are moving. Now, you wouldn't think ice would have like a temperature, like you could raise the temperature of ice because it's still ice and the particles are locked in place. Well, it's somewhat analogous to, yeah, you could have a room full of second graders named Timmy, and they could all be sitting at their desk, but that doesn't mean they're not doing this, okay, all right? Because we're gonna give them Skittles. So, we're not really gonna let the kids move around, but they're gonna start to fidget a lot more, okay? Come on, I can't imagine teaching you as a second grader.
It was bad.
Was it all
Yeah, it
in the
was
same
bad.
class?
Oh, yeah, pretty much.
Yeah. Was it bad?
Couldn't be
Yes.
that bad.
Oh, I
couldn't
think it
have
could
been
have
that
been.
Yeah.
He says it's not bad, then
I was
it's bad.
I was a good kid. You know what I had to clip down a grand total of 1 time.
You got what?
I had to like clip down.
Oh, you.
I had
one
I mean,
time.
like have these
Okay,
charts.
what,
like,
okay, I have no idea what you're talking about.
You've never heard of the clip chart?
Oh, God, no.
It's
Have we
where,
met?
like, I say we should use it in physics.
This is
Ooh, I like this.
Yes.
I'd be
Yes.
It still would be red every day.
Oh, we could have like absolute Kelvin or absolute Cohen.
Yes.
That's the one.
Yeah.
Bottom. That's the one. Very
Yeah,
bottom.
0 is absolute Cohen.
They typically do them in colors with like green is good, and then like if you do something good, you can like really good, you can clip up to like blue, and like down is like yellow, and then orange, and then red.
Did you say good? And then red's when they exit.
So where does everybody start? Like what's the
You start at green.
Everybody starts at green.
Everybody
Every
starts
day.
at green.
It doesn't matter what you did the previous day, you start at green.
Oh, it restarts every day?
Yeah.
Oh, that's disappointing.
I
Why not?
No, if I was a teacher, I'd seriously, I would write.
Well, the same thing is not red every day.
They
Say
say
you
you
clipped
would.
at absolute color.
Like, or they either, they like, at least call your parents.
Can't go
Okay.
any further.
So,
Below the red.
so you only clipped, so
Only
when you
clipped
move
down.
down, is it down like a lot, or
You typically have to do something.
do you have to like, is it like one color move?
Yeah.
Like, that isn't like shades of green?
I feel like you can jump and.
No, it's like
Move
one
down
color.
multiple depending on
There's
the
no
offender.
shades.
Okay,
Like, if I hit a kid, I'd automatically move down red.
Yeah.
That did not happen.
Charles the
Allegedly. Allegedly. All these allegations came.
God, you're
I didn't hit
aggressive in
anybody.
politics. Okay,
If I hit somebody, they wouldn't.
so, all right, in this problem, we're gonna make the ice, as you would put in your vernacular,
You should.
clip up, okay?
I clip, yeah.
So we're gonna clip up to 0. Now, at that point, the ice is gonna begin to melt. So now now the energy isn't gonna make the particles vibrate anymore. Now you're gonna begin to break the hydrogen bonds that hold the water molecules together. So the energy is still going in, but you're not changing the temperature. So this is why on this portion of the graph, you're gonna use delta T times mass times the specific heat. And someone pointed out that the specific heat value I gave you might have been a little bit different. That's because that's the one that this book used. So that's why I gave you that specific heat value. So anyway, so this is gonna get you the energy that it takes just to warm the ice. Then you've got to melt the ice, so then you've got to use that mass times the latent heat of fusion. And again, when you look at this, pay attention to the units. This is in kilograms, that's joules per kilogram. So the only thing that determines the amount of energy involved to melt ice, boil water, whatever that is just the mass, okay? The change in temperature isn't a factor because you're not changing the temperature. That's why it's called latent heat diffusion, or latent heat of vaporization. Whereas, once you warm that up, then you're changing the temperature, that's why that becomes a part of that. So, you gotta find the two different values of energy, and what you should see is that the, energy to melt the ice is literally, like exponent bigger than to warm the ice, okay? So like an order of magnitude bigger. So what you're gonna do is you're gonna find the total amount of energy, which should be an GPA times 10 to the 5th. Then you can figure out how much power that you've got, and then it's just a matter of making the units work out. So you can figure the power from PIV, because you got 5 amps, 120 volts. Then, and you know that power is just change in energy per unit of time. Now you know how much energy that you need. You know how much power that you have. So what unit should your answer work out to be? Seconds. If nothing else, make the units work out. Okay, cool, there you go. All right, are we cool with that?
What about the
What should be?
34B diagram, what do you want from me?
Hold on.
Okay.
What was your question?
What should 44B be close to?
In seconds, around 400. 400 and some change. Okay, Connor S., what was your question?
What do you want
Mr.
from
Oxford?
Diagram of 34B.
Like the example provided in that.
Yeah. So, on problem 34, so, don't make this complicated. I know. So, two identical are connected in series to a single night. Sketch the circuit.
No, not that one. B.
I think, or you can sketch the circuit first.
You could do that.
He's talking about, like,
You could
the
do both
tr-
if you want.
The,
Okay, just,
Okay. Don't be mad at me. Jacob told me.
That was okay.
I say we kill Connor.
What?
You said Connor or Connor?
Yes.
Yeah.
okay, diagram, good?
Yeah, I'm fine with that.
Yeah.
Okay,
Good enough.
okay.
Pass.
So on the diagram, let's say, which way, let's say go with the conventional current.
Okay.
So you're gonna start here with, and this is gonna be voltage, and this is gonna be like a function of time. So you're gonna start in here with these particles, whatever you wanna call them, greenies, I don't care, starting here. You're assuming that as they enter, they have no voltage. So that's gonna come up to some value of voltage, 120 volts, whatever that is, okay? Now, the key assumption is that as it moves through the wires, we're assuming that the wires have no resistance. So this is when it's in the battery.
Oh, we're still assuming that? Does it say assume ideal?
Well, unless you're told differently, you do, okay?
Okay.
So, this is when it's in the battery. If there were two batteries, you'd step it up in two different levels, okay? So, then it's gonna move through the wire, okay? So, if you assume that the batteries have the same resistance, then each one of those is going to reduce the voltage basically by a half. So you go through the first one, that drops it, you go through the second one, that drops it, and then, so this would just this cycle would just repeating. So that's all you have to have.
Okay.
Bueno?
Going down.
Oxford?
Alumni.
I'm just, oh, we're gonna start calling you OA,
Oh, eh? Why
How many
OA?
cycles?
Oxford alumni.
Oh, yeah.
How many cycles do you want?
Oh,
Just
Oh,
one?
just, you can just draw one.
Okay.
Draw 10 cycles.
Don't listen to OA.
Hey,
I would
Oh,
never
look,
listen to an
an
English
idiot.
Good call.
man. Yeah.
Yes, Jane Carroll.
33.
Okay. Problem
Oh, yeah, this
33?
one was a silly.
Yeah.
Okay.
32.
You have to get a little bit janky with the, so,
I got
It was, you can derive the formula.
how I
Mitchell, you
got
can
it.
derive it. I just had to like know what the formula was before I derived it.
I got the answer somehow, but I don't know.
Oh, I hated this one.
It's this one actually took me a
You
while.
have to like make it. I just made it like.
That's what I did, and I got the right answer,
Yeah.
but it doesn't make sense unit-wise.
Does that work?
What? Yeah, it does.
okay, so let's start with this, Jane Carroll.
Resistivity is.
So, this
Charles,
V, delta V over L is just a way of saying voltage equals L. Okay? Cool with that. So, if you solve this for your electric field, you get delta V over the length of the wire. D is the same thing as the length of the wire. So then, voltage equals IR, right? So all I'm gonna do is substitute, revert it up, right?
I think I did.
Now, you also know that resistance equals, so we're gonna rewrite this as I times rho L over A divided by your length. Does that make sense? Okay, so all I did was some simple substitutions. So, knowing that, then what's gonna happen to the length? Length cancels out. Got it from there? Okay. Yeah, that's just the assumption that you have to make. Charles, shortcut?
Well, I did it a really long, stupid way. Then.
what did
Okay.
you even do?
Yeah.
I mean, that's.
What did you do?
I just made length equal 1 meter.
Oh, okay, you can do that too. Guess what? It canceled out.
Yeah.
At least you chose wisely and you made it 1 meter and not like 0.532.
Yeah.
It's okay.
I would never mile. Wait, is that the? Oh no, it's not.
Yeah. a mile
Oh, wait, is that what you did?
Okay.
What? No.
Is that what you did?
I did it this way.
Not that way?
No, I don't
So
do it
what?
Charles' way, because Charles is not the brightest.
Ironically, this is a shortcut.
I didn't use it. So what? Yeah.
What are you confused about?
Equals V over.
T,
So,
No, V over L.
U for L, sorry.
voltage equals Ed,
Yeah.
right? So if you solve for the electric field, it's voltage over the length of the wire.
What are we finding? Oh, okay. Okay.
So on 33, this is why you tend to flip out, because you don't have the length. But if you substitute IR for voltage, good with that? And resistance is rho L over A, then your lengths cancel out. Charles, what are you batting your eyes at?
What? So E equals, okay. Okay, E equals V over D. Makes
And
sense.
then V equals IR, so you put IR over
So if you
D,
roll it up,
and then R equals rho L.
Oh,
over
okay,
A.
so you're just, okay. I think that makes sense-ish.
all I'm doing is just a series of substitutions.
Yeah. That's really complicated. Just smash
Oh, I'm
mouth
sure your
physics
method
is.
was simpler.
It was simpler. I only did one thing.
Okay. Anything else? Going once, going twice? Do those hand in hand. Danny's talking outdoor camera.
Okay.